their biennial update reports and national communications. And under the enhanced transparency framework of the Paris Agreement, the reporting requirements for uncertainty analysis are even more stringent and require a good data collection system and technical capacity in place. So there is a pressing need to strengthen the capacity of developing countries on uncertainty analysis. And this is justified by the large number of nominations that we received for this webinar, more than 1,000 nominations. This webinar will provide you with the knowledge you need to conduct an uncertainty analysis in your national GHG inventories. It will also help you understand how to use the outcomes of the uncertainty analysis to develop and prioritize your national inventory improvement plan. It's a very technical webinar, and we strongly encourage you to remain connected and participate in all sessions. We may not be able to respond to all your questions during the webinar due to time limitations, but we have in place a platform that we call GHG Help Desk that you can use to send additional questions. We will share with you the link to register to GHG Help Desk, and we strongly encourage you to make good use of it. We also plan to repeat this webinar later this year. In the agenda that we shared with you, the webinar is structured into 10 technical sessions and 2 hours each day until Friday. And you have the possibility on the platform to choose between English, French, and Spanish. And given the large number of participants, we invite you to write your questions, if any, in the chat box. We won't give you access to the mic, so you won't have the possibility to speak. The training materials will be shared with you later. So we hope you will find the webinar useful, and we wish you a very good participation. Thank you for your attention. Now I'm pleased to give a short presentation according to the agenda to share with you. Let me share my screen first. Yeah, I hope you can see my screen. Okay. So now I will give you a short presentation to share with you the reporting requirement for uncertainty analysis in national GHG inventories that you need to know when preparing your first BTR under the Paris Agreement. Because uncertainty analysis is considered a cross-cutting issue, I will show you most of the reporting requirements which are connected to uncertainty analysis and where uncertainty analysis is required. The first element I would like to remind you of is that parties under the Paris Agreement are required to submit their first BTR at the latest on 31st December 2024, according to Decision 18 CMA1, which means by the end of this year. Of course, least developing countries and small island developing states may submit the BTR at their discretion. And according to that decision, 18 CMA1, the use of the 2006 IPCC guidelines is mandatory. And you can read in the 2006 IPCC guidelines that uncertainty estimates are an essential element of a complete inventory, which means that an inventory which is submitted without uncertainty analysis may be considered incomplete. And uncertainty estimates should be derived for both the national level, the trend, but also for emission factors, activity data, and other parameters, and for each category. So you see the amount of work that is required for uncertainty analysis. So when preparing the BTR, it's mandatory to quantitatively estimate uncertainty and qualitatively discuss uncertainty for emission removal estimate for all categories, including inventory totals for at least the starting year and latest reporting year of the inventory time series. I will come back to time series later. It's also mandatory to estimate the trend uncertainty using at least approach 1. You will learn more about these technical terms during the webinar. But many developing countries have reported challenges, including lack of technical capacity, lack of good data collection system to conduct a good uncertainty analysis. And for those countries, the decision 18 CMA1 gives flexibility to provide at a minimum a qualitative discussion of uncertainty for key categories where quantitative input data are not available to quantitatively estimate uncertainty. And they are encouraged to provide quantitative estimate of uncertainty. In terms of time series, it's mandatory to report consistent time series from 1990 until the submission year -2 or -3 with flexibility. We understand that many developing countries have difficulties collecting historical data and even more recent data. And they have the flexibility, instead of reporting 1990 as starting year, to report data covering at a minimum the reference year or period year in their nationally determined contribution, and then a consistent time series from 2020 onwards. It's also mandatory to report recalculations for starting year and all subsequent years of time series, together with justification and impact of recalculations. So if the recalculations are triggered by the use of new method, new data, or for example, reallocation of emissions or removals, all these justifications must be reported together with the impact, whether the recalculations lead to increase or decrease in the time series. it's also mandatory to identify key categories for the starting year and the latest reporting year, including and excluding LULUCF categories, using approach 1 for both level and tone assessment. So like I mentioned, you will learn more about all these technical terms during the webinar. So key categories, as you know, are largest categories which together contribute to 95% of total emissions in the inventory system. But the flexibility given to developing countries here is to use the threshold 85% instead of 95%. So the intention is to provide developing countries with the opportunity to allocate more time and more resources to the most important categories in the inventory system. It's also mandatory to report on institutional arrangements, including planning, preparation, and management. But one key, as you know, one key function of institutional arrangement is data collection. And if the system in place is not able to collect data, it won't be able to support the ETF of the Paris Agreement, because the ETF is very demanding in terms of data. So a good data collection system in place is very important, and we strongly encourage countries to involve academia and also statistics office in the system, because those people, they have good background on statistics, and they can help on uncertainty analysis. It's also mandatory to develop a QAQC plan, including QAQC on uncertainty analysis. It's also mandatory to report 7 gases, including CO2, CH4, N2O, HFCs, PFCs, SFCs, and F3. And using the warming potential from the fifth assessment report of the IPCC. And the flexibility given here to developing countries is to report at a minimum the CO2, CH4, and N2O, and any F gases, including the NDC, or have been previously reported in the inventory. I have included here references to decision 18 CMA1 and 5 CMA3, and I strongly encourage you to read and familiarize yourself with them. They contain all the reporting requirements that you need to know for when preparing your national inventory reports under the ETF of the Paris Agreement. So I will stop here. I guess you have some questions, but like I mentioned, given the large number of participants, we only give you the option to write your questions in the chat box. So if you have any questions, please write them in the chat box, and we will try to provide some the answers. So I will stop here, and I will give the floor to Diego to start with the technical content of the webinar, and according to the agenda today, we will cover session 2, overview of uncertainty analysis, session 3, the causes of uncertainty, and then section 4, how to reduce the uncertainty associated with input data. So I guess Diego is connected. If you hear me, Diego, I hand over to you to continue with the webinar.
Hello. Yes, can you hear me?
I can hear you, Diego.
Great. Thank you. Thank you very much, Sabine, for the introduction to the webinar. Hello, everyone. My name is Diego Escurra. I've been working with national GAG inventories for several years, for more than 10 years, particularly in Argentina, in the Argentina National GAG Inventory, and working on the development on the inventories, but also leading the development of the uncertainty assessment of the inventories. So I have some experience applying the methods in IPCC guidelines for uncertainty assessment in practice. And I've been teaching also uncertainty assessment in undergraduate and graduate levels in the university, not related to GAG inventories, but uncertainty assessment is a general approach that is applicable to several areas in different industries. So it's you will find it very useful for not only for GAG emissions accounting and reporting. It seems some of you are not listening to me very well. Let me see if I can adjust the mic a bit. Let me see. Okay, let's see if now it's better.
Yeah, I can hear you.
Okay.
Yeah.
Thanks. Okay, so my background I studied engineering in the university. I did a master's degree in engineering in engineering, and I teach at the university. So in parallel to the working in the GAG inventories. So I will start sharing my screen. I guess I'm able to do that. I will try. Let's see if it works. So you should be all seeing the presentation. Do you see it?
Yes, Diego, I can see your presentation from here. Yeah, okay. So I see a lot. Yeah, okay. So that confirm that you can see. Okay, we can move on.
Great, thank you. So we will be together the whole week just to discuss several aspects of uncertainty analysis related to national GAG inventories. And we are doing this because we've seen that particularly in developing countries, we've identified several problems while trying to account for the uncertainty of national GHG inventory. These are just a few of the problems we identified. The first, I would say, in my experience, the first 3 or 4 are the most common problems in developing countries. The first one is very, very common, and it's related to lack or limited resources to develop the GHG inventory. That means that in many developing countries, the priority is always on the inventory. We are running to try to get the inventory, the GHG accounting ready so we can submit and comply with the reporting commitments for our countries. So we put almost all the resources there to quantify the emissions and removals. So the further assessment and the uncertainty assessment and the improvement of the cycle is generally not done, because we are always trying to comply with the reporting requirements, with the minimum requirements, because we don't have enough resources. That's the most common problem we've identified. Another problem is that doing the uncertainty assessment of the national GHG inventories requires knowledge of statistics. It requires background, it requires understanding the basic of statistics, confidence intervals, probability distribution functions, and several aspects that are not necessary for the inventory itself, for accounting itself, the emissions. So it's not so common to have some staff in the team with that background. And the third and fourth are related to the availability of information to do it, because you may have resources, you may have the staff, you may have staff with statistical background, but if you don't have the information to quantify the uncertainty, it's very difficult to do it. So those are the most common problems. I would like if any one of you would write in the chat 1, 2, 3, 4, 5, 6, which one of these you think represents the situation in your countries, so we can have some kind of poll, some kind of online assessment of your particular case, because we will try to go through all of them during the week. So you are invited to say which one or which ones you are most confident that that's the situation in your particular country. During the webinar, we will go through the IPCC guidelines in several levels. We know that many of you may already be working with uncertainty assessment. You may have already done uncertainty assessment for GHG inventories. You may have a lot of statistical background. So some parts of the webinar you may find not so interesting, because we are trying not to leave anyone behind. So we are covering all aspects of uncertainty assessment, from the very basic to intermediate level, and some higher level and very detailed and specifics for particular situations. So for those of you who have experience, I would like you to do two things. First, share your experience if you think you can provide some useful information for the rest of the attendees. And the second, be patient for those parts where you know or you have enough background to understand that situation. So be patient for those sessions or part of the sessions. Because we also acknowledge that some of you may have not ever been involved in the uncertainty assessment for the inventories. So it's very important that you all leave this webinar on Friday by understanding all the basics, all the terminology, all the implications, the importance of the uncertainty assessment, what you can do with the uncertainty assessment once it's done for a GAG inventory, and being able to actually perform the assessment of the uncertainty of the national GAG inventories for your countries. So we will go through the 5 days of the webinar. Today and tomorrow, we will focus on the basics of uncertainty. We will understand the terminology, we will understand the causes of uncertainty, and we will try to learn and understand how to get the data to build the uncertainty assessment for the national GAG inventories. Then on Wednesday and Thursday, we will use all this background and all this information, and we will start combining the individual uncertainties using two different approaches. On Wednesday, we will use approach 1, propagation of error. And on Thursday, we will use approach 2, Monte Carlo simulation, to combine the individual uncertainties and arrive to the uncertainty of the national inventory. And we will complete the webinar on Friday by 3 sessions where we will explore the hybrid combinations of approaches 1 and 2. We will see how we can use the uncertainty assessment to identify key categories for the inventories. And we will try to learn how to quantify the uncertainty when you have missing data, when you have data gaps that you have to fill, you have to put some values, and you use some splicing techniques to fill data gaps. You are introducing uncertainty in those estimates. So we will learn how to assess the uncertainty of those techniques when we are filling data gaps. So let's start with the first session. The first session, it's related to overview. Today, we will try to make sure that all of you know where to go and find the information you need, because in a year from now, when you are finishing the inventory for your countries and need to assess the uncertainty, you may not remember all you learned in this webinar, so you will have to go through the relevant sections of IPCC guidelines to get the details and the specific information you need. So we will see where the references are. We will understand the terminology we will use all across the week, and we will make sure we understand the difference between accuracy and precision, because the assessment of each of those is different. So let's start with the first one. The overview of uncertainty in IPCC guidelines. This is the 2006 IPCC guidelines, the structure. You know that the guidelines are divided into volume 1, that's general, it's a cross-cutting volume. And then you have the specific volumes for energy, industrial products and product use, AFURU, afforestation, forestation, and other land use, and waste. So the guidelines are divided in sectors in each of the main sectors of the inventory. And in the volume 1, the guidelines, you will have the specifics of uncertainty. In chapter 3, in chapter 4, related to key category assessment, and in chapter 5, related to splicing techniques. When you have data gaps, you have to fill. And in parallel to the IPCC guidelines, you will also find a lot of very useful information in the good practice guidance and uncertainty management in national GHG inventories. It's a whole publication related to uncertainty, and it's distributed also in the main sectors of the inventory: energy, industrial processes, agriculture, and waste. And it provides guidance and examples to quantify the uncertainties, the choices, how to recalculate the information, and do the quality assurance and quality control for the inventory. So this is the reference. You will go every time you need more information. You can go to each of the volumes here. So let's start with the overview. So what is uncertainty? To start speaking about uncertainty, we need to understand what uncertainty is. And uncertainty is basically that we don't know the true value. So we are accounting GHG emissions, we are accounting removals, we are accounting a lot of different values, activity data, emission factors, some other parameters. And the reality is that we don't know the values. We use some values. In general, we use average, but the average, it's not the true value. And that's something you have to really put in your hands, in your heads, because it's very disturbing to realize that the values we are using are not the true values. You don't know the true values, so you are using your best guess for those values. And when you realize of this situation, you understand that that's not enough. It's not enough to know the best guess of the values. You need to know the uncertainty of those best guesses. So we will learn how the IPCC describes these best guesses and the uncertainty of these best guesses while we account for the emissions. And that's what uncertainty analysis is, trying to identify what's the best guess for each of the values and what's the range that could take for those variables. We need to understand and to assess the variability of this best guess to get a range that includes this unknown true value. And the IPCC guidelines describe this by applying the 95% confidence interval. That's how uncertainty analysis is defined in IPCC guidelines. And a small difference that was introduced in the refinement of the IPCC guidelines in 2019, it's the concept of uncertainty assessment, because uncertainty analysis was defined as a quantitative exercise. But we know that assessing the uncertainty, it's not always possible to do it quantitatively. So there are some components of the uncertainty that you cannot quantify with these techniques we will go through during the following days. So the term assessment includes quantitative and qualitative assessment of uncertainty. So this is the general approach. If we see, I guess you can see the pointer. The basic GHG inventory structure starts with the conceptualization. We identify the sources, we identify the data we have, we identify the tier we will use to quantify the emissions. That's the conceptualization stage. Then we collect all the information we need and we calculate the emissions or removals. That's the basic cycle. Now, what we are including here is the uncertainty associated with all this process that includes the input uncertainty quantification. That means for all the data collection, you also have to get information on the uncertainty, not only on the best guess, but also on the interval describing the 95% confidence interval. For all activity data, for all the emission factors, or any other parameter that is involved in the calculation, you have to assess the uncertainty at the 95% confidence interval. And when you have done that, you have to combine the uncertainties. Every individual uncertainty for each parameter is combined in the calculation. Parameters, activity data, emission factors are multiplied, they are summed, they are divided, there are a lot of equations that combine those parameters, so the uncertainty is also combined there. So you have to combine the uncertainty for all the parameters, and the IPCC guidelines provide two approaches. Approach one, that it's linear error propagation. We will go through this on Wednesday. And Monte Carlo simulation. It's a simulation technique. It's very, very interesting. We will go through this on Thursday. And once we've combined the uncertainties, we have the result of the inventories, the emissions and removals, and we also know the uncertainty associated to these emissions with the concept of knowing the 95% confidence interval. So that's what we are trying to do with uncertainty assessment. But there is always a but. That's not all, because if we close the process here, we will just do the same every year without further improvement. So what we want to do is to use this information to identify the key data, the key categories, the key parameters, the activity data, the emission factor, which ones of the parameters we are using in the inventories, which one of those are the ones that contribute the most to the total uncertainty. So, because you may imagine that it's not possible for any human being to improve every single parameter of the thousands of parameters involved in any calculation of GHG inventories. So it's very important to identify which ones are key and assign resources to those parameters. We can improve either the conceptualization of the inventory or the data collection, so we can improve the estimates of emissions and the estimates of uncertainty. So let's start now with some key concepts of uncertainty analysis. We've gone through confidence interval during this introduction, but we will use it a lot because it's the key concept for uncertainty assessment. So what do we mean with confidence interval? We mean that we want to understand a range. We want to understand the range for each variable, the range of the values that this variable may be assigned, so that when we use the best guess, we also know to which extent this variable may be higher or lower to this best guess, considering a 95% confidence interval. So we are very, very confident that this interval contains the true value, which we don't know, and because we don't know it, we are using a best guess. So that's the confidence interval, and we will define uncertainty for each parameter based on this confidence interval. But knowing the confidence interval only provides us with the information of an upper limit and a lower limit. And we know that within those extremes, the probability of the true value to be contained within those values is 95%. But we don't have the information of how the probability is distributed for those variables, for those values. So to know that, we need the probability density function. The probability density function describes the probability, the range, and the likelihood of each of the values within the range. It's generally described. We will go through it when we use the approach to Monte Carlo simulation. We will use probability density functions to propagate the uncertainty of each of the values. And then we will use also the sensitivity analysis. It's a method that it's very important to set priorities, to understand which variables are the most important, which variables deserve more resources to improve the accounting of the inventory and the uncertainty. So now we've gone through these key concepts of confidence interval, probability density functions, and all those things. We will try to be clear on the difference between accuracy and precision, because this may look some trivial to many of you, but it's not so when you are dealing in real life in your daily activities with data and results of your inventories. So the main issue with accuracy and precision is that the uncertainty is assessed completely different. When you are dealing with accuracy problems, you are dealing with bias. You are dealing with a best guess estimate that is not representative of the reality for your case. So you may have a very, very good and precise best guess, but this value is not representative. So then you have a problem of accuracy. You are not accounting properly, perhaps, the concepts of the emission source you are trying to quantify. It's related to systematic errors. It's related to something you do repeatedly in a way that bias the result. On the other hand, and that's the accuracy, it's not resolved with propagating the uncertainty of the variables. You have to change some structural assumptions to correct, to modify accuracy problems. While precision, on the other hand, it's related to the variability of some data. It's this confidence interval that we are not sure, we don't know the true value, but we know that it's contained within a range and could be any value within that range. That's a problem of precision. Larger ranges, when the upper limit and the lower limit are very far apart from the best guess, you have a problem of precision. You have a very broad range, and to correct this, you have to there are different strategies. We will go through some of them today, but it's generally related to the variability of the values. So perhaps the best guess is very, very close to the unknown true value, which you will never know because you don't know the true value. But the best guess may be very close to the true value. But the reality is that since you don't know the true value, what you know is the best guess and the interval of the 95% confidence level. So it's very imprecise, the best guess. So this is a very common picture of the difference between accuracy and precision. You see in the first case, A here, this is a very clear picture describing a very precise method, a very precise result that completely a very precise method, but completely inaccurate. It's completely biased. You see, all the values, the confidence interval, that you could understand it as how big this black dots are, how far are each one from the other. It's very precise, but it's inaccurate. And on the other hand, in figure C, you see this is quite imprecise value. The dots are far apart from each other. But if we use the average of these values, the average value is very, very accurate. It's very accurate. So when we have problems of accuracy, we are dealing with A and B. And when we have problems of precision, we are dealing with B or C. The ideal situation would be D, figure D, when we have very precise values and very accurate estimates. The best guess is very accurate, and the precision, the confidence interval is very narrow. That's the ideal situation we would like to have to all variables. This is the same picture, but linked to the probability density function, because in reality, when we have data, and if we have historical data to which we can assess, we can see probability density functions. We can extract from the data, we can create some figures to see the uncertainty in the form of a probability density function. So when we have low precision, we have these cases that the probability density function are wide, and when we have high precision, the confidence, the probability density function is very narrow. The values contained here, the probable values that the variable may contain, are very narrow, or are contained in a very narrow range. And on the other axis, we see the accuracy. This is low accuracy, the best guess, the central value of the probability density function are not matching the true value. So the best guess is biased. And when we have high accuracy, the best guess matches the true value. But again, the problem is that in reality, we don't have this dot line as reference to see where the true value is. All we have is the data, the variability, the distribution, the probability distribution function, and the best guess. That's all we have. So we need to assess if we may be dealing with a problem of accuracy or not. It's very easy to realize if we are in a problem of precision because we see the variability in the data, but it's not so easy to identify accuracy problems. So the first part of assessing the uncertainty of a GHG inventory is trying to assess and remove all biases as possible as in the estimates, to make sure from that point onwards all the values we get and all the information we deal with is not contaminated with accuracy problems. It's very easy to say, it's very difficult to implement because we have the information we have and we have to deal with that. So it's very important to assess the categories, and it's very important to do it following the key category assessment because it's very demanding to do it. So we cannot do this for every single subcategory or 3 or 4th level category in the GHG inventory. We need to understand where to assign resources so we can do this efficiently. So the quantitative assessment, the quantitative analysis of uncertainty, it's what we will work with during the following days. And it's related to random errors, it's related to precision. Accuracy is related to concepts, the conceptualization of the uncertainty, the conceptualization of the methods we are using to calculate the GHG emissions. So let's start with putting some numbers and understanding the terminology we will use to quantify the uncertainty. So we define the confidence interval as the range that encloses the true value, in this case with a 95% confidence interval. So we know that within this range, there is 95 confidence that the true value is in there. Can the true value be outside the confidence interval? Of course it can. Of course it can. It can. But there is a 5% probability that the true value is outside this confidence interval. So that's very important to understand. If you ever manage to get a much better estimate of a parameter, and you find that this value is outside the original 95% confidence interval, that can happen. It's not wrong. It can happen. That means that your previous estimate was inaccurate and imprecise. You may have a bias problem, and you may need to correct the accuracy of your estimates so that the true value is contained, the new confidence interval contains the true value. So how it's reflected in the uncertainty assessment? Well, we have different cases. Let's start with a symmetric case. Let's see, for instance, that the best guess is 80, and we have the confidence interval containing 80, ranging from 64 to 96. So how we describe this value is described as the best guess plus less the distance between the limits of the interval and the best guess. So the distance between those values in this case is 16. So in absolute terms, we will say that this variable is 80 plus less 16. That means we are using 80 as the best guess, but the variable may move from 64 to 96 with a 95% confidence interval. And we can also express this, show this in relative terms, meaning that 16 related to 80 is 20%. So the confidence interval is 80 plus less 20%. This is very simple way of showing the uncertainty, and it shows that we don't know the true value. We know the range containing the value at a 95% confidence interval, and we are showing our best guess for this variable. So this 20% is what we will use to quantify the uncertainty. IPCC guidelines for national GHG inventories applies the concept of uncertainty in relative terms. The propagation of the uncertainty of the variables are always in relative terms. So we will assign uncertainty in relative terms, 20%, 10%, 5%, 50%, 100%. We will assign the uncertainty as a percentage of the mean, and we will use this uncertainty to propagate and combine to reach the uncertainty of the inventory. So that's the use of I that IPCC uses for uncertainty. It's relative terms. It's very important from now on that you understand that when we are talking about uncertainty values in IPCC guidelines, we are referring to relative values of the uncertainty. Then we have asymmetric cases. Some variables will not follow a symmetric distribution, may have asymmetric confidence interval. So we will have to define the lower limit and the upper limit separately. So in this case, the best guess is 80, but the confidence interval may range from 72 up to 104. This means that we can describe uncertainty as 80 minus 8 plus 24, or in relative terms, minus 10% plus 30%. It's very, very common to find values that are asymmetric. Most of them related to emission factors, because emission factors are in general non-negative. So the confidence intervals will generally have a longer tail to the upper limit and a shorter tail near to zero, or to the left side of the values. So it's very common to have asymmetric intervals. And then we could just keep this and acknowledge the difference between symmetric and asymmetric intervals. But in reality, we may have information, variables, data that it's very, very uncertain, that the confidence interval is very wide. It's a huge uncertainty. And for those cases, it's kind of difficult to understand the uncertainty when it's expressed in relative terms. If I tell you that a variable has an uncertainty of 20%, you all understand the uncertainty of this variable, the range of this variable. But if I tell you that a variable has an uncertainty of 400, you need to think for a few seconds to understand what it means, to which values this variable may take. So it's not so intuitive when the uncertainty is very large. And for those cases, you will find in IPCC guidelines reference to uncertainty as factor of a number. For instance, in this example, the mean value is 100, and the confidence interval ranges from 50 to 200. That means that the uncertainty in relative terms is minus 50% plus 100%. That's the same of saying that the value is 100, but it could be half of that value or double that value. It could be half, 50, or it could be double, 200. So we could just say that the uncertainty for this factor, for this value, is a factor of 2, double or half. And this applies to any other case. You can have factor of 3, factor of 4, meaning the uncertainty is 3 times higher, 4 times higher, or a third of the best guess, or a fourth, a quarter of the best guess. It's very useful. If I tell you a factor of 2, you immediately understand what it means. So let's do some exercises. Let's try to apply this confidence interval and relative uncertainty to derive the uncertainty of some of the parameters. I guess you all recognize this table, the emission factors for fuels, for combustion of fuels. Let's focus, for instance, in fuel oil, residual fuel oil. When we go to the IPCC guidelines, we see the default emission factor and the confidence interval. We see the lower limit and we see the upper limit. Can any one of you just calculate the uncertainty associated to this default emission factor? The emission factor for residual fuel oil is 77,400. So I want to know the uncertainty in relative terms associated to these parameters. If you can calculate it, you can just put it in the chat, and then we see. I want to make sure we all understood this concept of relative uncertainty. It's quite simple, but yet very, very important. So, because we will use this from now on until Friday, and you will use this to quantify the uncertainty of the inventories in your countries. I see in the chat. My question was that I want to understand the uncertainty in relative terms for the emission factor of the residual fuel oil, which is the value that I should use to quantify the uncertainty for this parameter. I see there minus 2.5 plus 1.8%. That's Julian. Okay, I guess that was quite easy. So what you probably did was to understand, to calculate the difference between the upper and the lower limit related to the default emission factor, and then calculate it as a percentage, less 2.5% plus 1.8%. That's okay. One thing we need to understand is we need to understand that uncertainty assessment, getting the uncertainty data of the parameter, it's also uncertain. It's also uncertain. So it's very important to know that we want to understand the level of uncertainty, and we are not interested in having a very detailed figure for the uncertainty. So I really don't care if the uncertainty is 1.8, 1.83, 1.8321. I don't need so many digits for the uncertainty. I need to know if the uncertainty is around 1%, 2%, 5%, 10%, because otherwise I would need to do an uncertainty assessment of the uncertainty calculation, which is ridiculous. So we are okay with a value that represents the uncertainty of a figure. In general, as a rule of thumb, we will try to use one digit for uncertainty, or at least two. So we could easily see here, it's clear an asymmetric case, but it's not so asymmetric. So we can kind of agree that we could use and propagate the uncertainty for this emission factor, applying a 2% uncertainty for this parameter. We could use 2.5. We could, if we want to be more conservative of the uncertainty and do not underestimate it, we could. But in general, when the asymmetry is low, it's okay. We kind of assimilate the variability to a symmetric case, because the propagation of the uncertainty, at least under approach 1, we will go through on Wednesday, assumes symmetric variability. So in this case, we could say that the uncertainty for this value is 2%. What about the emission factor of methane? What about the emission factor of methane for residual fuel oil? What's the uncertainty of the values? The best guess we are seeing here for IPCC in the table is 3 kilograms of methane per terajoule of fuel. So what would be the uncertainty in this case? The uncertainty for methane of residual fuel oil. What would be the uncertainty here? Could you come up with a figure for this case? I see a few there in the chat. If we repeat the same calculation we did for CO2, we will see that the lower limit and the upper limit, it's very, very asymmetric related to the best guess. It's very, very asymmetric. So we can say the uncertainty in this case is minus 67% plus 233. That's a wide interval. Or that's okay if we are using the relative values for propagating the uncertainty. We will have to use these figures in relative terms, but this also means that this parameter has an uncertainty of a factor of 3. You could see approximately a factor of 3. So the best guess, 3, could be 3 times higher, approximately, so around 9, in this case 10, or 3 times lower, 1, it could be 1. So this is a typical case of a very asymmetric parameter where we can assess the uncertainty applying the concept of factor of a number, in this case, factor of 3. Okay? And we will see a lot of cases if we read different sections of the uncertainty assessment in the, I don't know if you explore it, but in the IPCC guidelines, for each of the categories, you will have the structure of the tier 1, the general description, tier 1, tier 2, tier 3, the parameters, the data, the emission factors, and then you have the uncertainty section for these specific categories, to which you can explore default data on uncertainty for the parameters involved in the calculation. So when you read the IPCC guidelines, you will see references to this factor describing the uncertainty of the parameters. You see a factor of about 2, that's, it could be 2 times, it could be double or half, a factor of 3, factor of 2, factor of 4. So there are a lot of references in IPCC guidelines that describe uncertainty using factor as a way to simplify the description of the uncertainty. So we here see what we mean with symmetric or asymmetric distribution. This is a typical case, a normal distribution that is very symmetric. And this is a typical case where you have the asymmetric uncertainty with your best guess and the lower limit and the upper limit. In this case, this is skewed to the right. So it's like this tail is pulled from the right, creating higher values in the upper limit than in the lower limit.
Yeah, Diego, excuse me. There is a request to explain more about factors. They say it's still not clear. Can you spend a few seconds to explain again?
Sure.
Yeah.
The factor, the way we describe factor to describe uncertainty is that what we mean is how many times the best guess can move up or down to reflect the confidence interval. The TF, I think this is a question of, let me go back. TF, it's the percentile, it's the 2.5 percentile and 97.5 percentile. It means that you have 2.5 percentage to the left and 2.5 percentage to the right, and in between you have the 95% confidence interval. That's the TH that's next to the confidence interval. The factor, the concept of factor is this. A factor of 2 means that your best guess, that in this case is 100, can be multiplied by 2. So it could be 200, as you can see in the confidence interval. Let me grab a little. This best guess can be 2 times higher, so it's 200, or it could be divided by 2, meaning that it could be half. This is what a factor of 2 means. It could be double, or it could be half. It could be multiplied by 2, or it could be divided by 2. In this case, with the emission factor of methane, we could say the uncertainty for this parameter can be described as a factor of 3, meaning that this 3 can be multiplied by 3 approximately in this case, leading to 9, or in reality 10. That's the confidence interval. It's approximately 3 times higher or 3 times lower. It could be divided by 3, leading to the lower limit of the confidence interval. That's the concept of factor. The concept of factor, it's not exclusively when it's asymmetric, but it could be used to any case, but in general, it's related to asymmetric because it's related to the geometric mean. If you remember something from statistics, we will go through it, some further details about this when we see the Monte Carlo simulation approach too. But when you have asymmetric cases, the best guess can be several values, because you have the average, you have, which is the arithmetic mean, you have the geometric mean, you have the median of the distribution, you have the mode of the distribution. There are several values that could be used to describe the best guess. So the concept of using the factor of 2, factor of 3 is related to the geometric mean, and it's very important in asymmetric distributions. Because in symmetric distributions, the mean, the mode, the median are all the same value because it's symmetric. So with that, we'll conclude the first part, session 2. That's trying, and I spent more time on purpose on session 2 because I want to make sure that we all understand how to identify the uncertainty in IPCC guidelines, what we mean with uncertainty in relative terms when we start to apply this and propagate the uncertainty. So let's move now to session 3.
Yeah, Diego,
yes,
just to alert you that we still have 30 minutes to conclude today's session.
Yes,
yeah,
thank you.
Yeah.
Great. So in session 3 and session 4, we will explore how to deal with uncertainty. Why data is uncertain, how to identify the causes of uncertainty, because if we identify that a problem is accuracy, we will have to apply different techniques than if we identify that the cause of the uncertainty is related to precision. So depending on the cause of the uncertainty, we will improve our estimates one way or the other. So that's the idea of session 3. And when we try to understand why the data we are using is uncertain, I think if you have been involved in developing national GHG inventories, you will feel very, very deeply hard in your heart what we mean with uncertainty in data. We need to get a lot of information from national statistics, from parameters, for efficient factors, representing the emissions of a sector, of all the sectors in the economy, with completely different models, different structures, different everything. So we will go through the main sectors and try to identify the main causes of uncertainty that are described. There are several causes of uncertainty. You can go to the IPCC guidelines and see the description of all of them. We will go through them. But imagine you have to, just to know the number of animals that you have to use, the number of heads you have to use for calculate the emissions of one of the sources in, I don't know, enteric fermentation or manure management. How many animals do you see there? Are you sure you can accurately define the number of animals that are in the country, in every regions, and differentiated by age, by diet, by, I don't know, whatever animal characteristics you may need to differentiate that, it's not extremely different. It's impossible. That's why all the data we have contains some uncertainty. Low, medium, high, but all the information we are entering in the inventories is data that contains uncertainty. In forestry, that's one of the most difficult sectors to quantify uncertainty, because there are a lot of variables that you need to take into consideration to understand how much carbon is stored in a forest, in a agriculture plantation. So there are a lot of issues we don't know, and we try to best guess the numbers. In best guessing those numbers, we end up with values that are uncertain, and we need to understand how uncertain those values are. In industry sector, the venting, the fluids that are in the circuits, in the pipelines at different stages, before a reformer, after a reformer, in a flare, in a venting stack. What's the composition of the gas? How many fittings are? Is the gas leaking in any part of the plant? So it's very, very difficult to get accurate numbers. Waste treatment, the composition of the waste, the treatment, the climatic conditions, how much of the waste is decomposed anaerobically, how much is decomposed aerobically, how much degradable organic carbon is contained in the waste, how much of it degrades aerobically. It's impossible to know all the values. So that's why we have uncertainty in every single value you use, unless we are multiplying by 2 or using some value that you know for sure. All the rest of the values, even if you measure it, there is uncertainty there. So these are the main causes of uncertainty described in the IPCC guidelines. So these are 8 causes that are identified individually that are sources of uncertainty in national GHG inventory. Some of them are related to bias, some of them are related to random errors, but in general, most of them may contribute to bias or random errors. It means to accuracy problems or to precision problems. So we have, for instance, lack, let me go back to the pointer, lack of completeness. If you don't have the full picture of a sector, it's very, very likely you end up with a biased estimate, because you don't have all the information to make sure that the best guess is representative of the situation. Depending on the model you use to quantify emissions, you may introduce bias because of the model, or you may introduce random errors because of the parameters you are including in the model. When you don't have enough information, there's lack of data, it's the same. You may introduce bias or random errors. If the data you have, it's not representative, that's a typical case of bias, a bias estimate. When you do sampling, when you don't know, it's impossible to know all the population, so you don't have the data from a census, and you have to apply to use a sample, to do a survey. It's a typical case of introducing random errors to the estimates. If you have measurements in general, if the measurement, it naturally contains some variability, it's very easy to identify random errors in measurement instruments because in general, they are part of the technical specifications, the accuracy. In general, it's related to accuracy, but it's described as a technical parameter of the instrument plus less 2%, 5%, 10%. That's very easy. But the instrument may be, the measurement may be done at a place that it's not representative, for instance, so you are introducing some bias in the results. When you misreport some information, so you report the emissions of one category into another one, you are introducing a bias to that category. Or when you have data gaps that you have to fill, you may introduce bias if the splicing technique you use is biased, or you may introduce, in general, you introduce random errors by filling those data gaps. So let's go through a few examples of these 8 sources of uncertainty. And it's very important because if you have not done any uncertainty assessment up to now, the first step you have to do is this one, is try to identify to the key category. You probably already have a GAG inventory. You probably already identify the key categories based on level, the approach 1. So you know which are the most important categories in your national GAG inventories. So next, what you should start doing to start with the uncertainty assessment is to start to identify for those key categories the type of uncertainty you may be facing. The problem, if you may be facing some bias problem, some accuracy, or if you may be facing some precision problems, some random errors. So in general, when you have, for instance, in energy sector, you may not be reporting some emissions, for instance, the coke production for steel and iron, you may not be reporting coke production emissions, associated emissions. So that's a typical case of bias result for that sector. In product use, fluorinated gases, perhaps you are reporting some gases, but not all of them. Some of them may be misreported. So that generates a bias. If you, in every inventory, every year, you only report a portion of the fluorinated gases, you end up with a biased result for that sector. Or if you do not discriminate in enteric fermentation from cows, so you may not have the emission factor for some or for other, or you may not have the information for discriminate or to apply the specific factor for different type of cattle, you may end up with bias. Or if the national statistics do not report some products, some industrial wastewater, for instance, that it's not reported in the national statistic, all those lack of completeness in the information you are using leads to biased results. When you have a lack of data, you may be introducing bias and random errors. So for instance, if you are using the national energy balance, that it contains provisional data, not that it was not gone through quality assurance or quality control process, but they are publishing some provisional information. You may be introducing bias or random errors by using those figures, or you may have to use the national statistics, for instance, that do not publish the cement production differentiated by type of cement, perhaps, or in AFLU, you may not have the statistics covering the different categories of animals. You may find some animals that are reported and some animals that are not, or some categories that are grouped and contain different animal categories all together and are reported all together. So these are the, or when you extrapolate, for instance, the amount of waste, that's a very common situation when you don't have very good statistics on municipal solid waste entering the disposal sites. One way of dealing with this lack of information is deriving the amount of waste based on the population in the country, but the population in the country in generally is 2, 3, 4, 5, 10 years old, so you don't have updated information on the population unless you've just gone through a national population census. So you have to extrapolate the population, and in this case, you may be introducing bias or random errors from the extrapolation itself. Sorry, I think I passed two altogether. So another case would be the representativeness of the data. It's the typical case of biased results. When the data you are using is not representative of the situation you are trying to describe, it's biased result. So for instance, you may be using some test from a laboratory for deriving the emission factor of a fuel in a vehicle, but that test the conditions of this laboratory test may not necessarily represent the conditions under which the fuel is being used. So the real driving conditions may lead to different nitrous oxide emissions. So that's a typical case of biased result. Or when using the efficiency of a production plant, for instance, steel production, and the data you have is based on full load capacity, but the plant, it's not operated on full load capacity along the year. It varies along the year, so you may be using some data that is not representative of the real situation in that country for that plant, or that, for instance, if you do some sampling in the biomass growth rate or the soil organic carbon or wherever you measure in a forest, for example, or in a plantation, you may do some sampling, but if the survey is not done well, if it's not representative of all the regions, the climatic conditions, the management techniques across different regions, you may end up with an estimate from this survey that it's not representative of the country, the whole country, so you end up with a biased result. Or in the waste sector, when you have, in general, old plants tend not to have enough information, while newly built plant it's more common to be more sophisticated, to have more control system, to have more data available. So if we base the efficiency of a wastewater treatment plant that's newly built, and we apply this efficiency to all the wastewater that is treated in the country, we may end up with a biased result because that may not be representative of the situation of the rest of the plants. So another case that's very typical for random errors, it's when we have random sampling. It's when we have some limited data, we have a sample from a population, and we calculate the mean value, we calculate the variability as the standard distribution, and all the statistical parameters, the variance, and whatever. But if the sampling is not done correctly, we can end up with bias or random errors. For instance, in industrial product and product used, the amount of glass recovered depending on the glass type, you have to apply different factors. There are different conditions for different type of glasses. So if it's based on a survey, you need to make sure that you are using a representative survey to remove bias, and that the survey is broad enough to reduce the random errors, to make sure that the average value from the sample is representative of the value for the whole population. Or in AFRU, the carbon store in a forest, again, you will do a survey. You need to set some sampling strategy to measure or to derive the amount of carbon stored. And if you measure few trees, you may end up with a large random errors. And if the trees are not representative of the rest of the population, you may end up with a biased result. Or in municipal solid waste, when the distribution, when you have information just for a few cities, that's something that's very common. There are some cities that contains very good statistics, and some other cities that the statistics are not so good. So if we, in general, we tend to use the data, we have more information, but unconsciously we may be introducing some bias by doing so. So we need to understand and be conscious on the source and the representativeness of the information we are using. That's the end of session 3. So once we have gone through these causes of uncertainty, we have 15 minutes to complete the first day of this webinar by learning some strategies to deal with uncertainty, and understand, very important, because this is one of the main objectives of uncertainty assessment, to set priorities. How to set priorities to improve the future inventories continuously. So each single cause of uncertainty, the 8 causes of uncertainties we've gone through, we'll try to explore how to reduce the uncertainties, some strategies, what we should do, what we should look to improve the quantification. Whenever we have bias, we have to go to the concept of the source. We need to understand what the source is about, which type of information we require, which type of information we know, and see if the concept of the approach we are applying to quantify this emission source, the emissions of this emission source, are adequate and representative of the information. So we need to see if the data we have is enough to understand the source of the information. And it's a way to reduce the bias for this type of sources is during quality assurance and quality control. In general, when we do that, we try to compare the result with other estimates and see if we find some inconsistencies among some variables that should kind of be similar or move in the same direction. So in QA/QC stage, we may identify some bias problems and create a task for a future inventory to improve the conceptualization of that source. When we are using a model, again, it's kind of related. We have to see if the model is adequate, if the concept of the model reflects the reality. Some models, in general, models are a simplification of the reality, and some of the simplifications are okay, but some other simplifications may not be representative of the real situation. Models tend to ignore asymmetry. Models tend to ignore non-linear relationships. Models may tend to ignore correlation between parameters. So we have to understand, if we are using a model, if the assumptions under this model are representative of the situation we are trying to describe. When we have lack of data, one of the best ways to fill these gaps is go and ask to people who know, consult the expert judgment on the information we are lacking, asking the experts that are working on those sectors that have expertise and can tell us if we may end up with a best guess that is biased, or if the range we are using for the uncertainty is good enough, if it should be broader, or if exaggerated and could be reduced because of the conditions for that sector in the country. So the expert judgment is a very, very, very good way of resolving lack of data problems. For the representativeness of the data, again, it's during QA/QC. It's very common to identify bias problems in that stage and to cross-check with other data and make verifications of the results against other results. For random sampling, random errors, the typical case here is to go to the statistics and work on the size of the sampling. The representativeness of the sampling and the sample size is what defines the random errors for a survey. So working on sample sizes, we can improve the accounting of random errors for a parameter. When we have measurement errors, again, the QA/QC or verification against other data, it's very, very, very important. It's very easy to identify if there are measurement error that contains bias in this case, because if it's measured, you have the information and it should match other parameters that are obtained with different means. So when we use this verification, in general, during QA/QC and cross-checking with other data is the best way to identify bias problems. Misreporting, also when we report the inventories, the categories in each of the subcategories, it's very important we report it correctly and follow the IPCC guidelines on which category and subcategory should all the sources be reported on, because this is very common for energy and industrial, very common to duplicate emissions or underreport some sources, or in AFLU and industrial with urea production and use or those kind of things. It's very easy to misreport data. So we are, and the problem with this is that when we misreport, we are creating bias in two different categories. One that it's higher than should be, and another one that it's lower than should be. But the good side, it's a little easier to identify those misreporting, because if you follow the guidelines in IPCC where to report each value, you shouldn't have a big misreporting issues. But it's one very common source of bias. And when we have data gaps, use the tools, the statistics tools, to understand if we may be introducing some bias depending on the source of information. We will go through this tomorrow on statistical assessment for data, and on Friday when we have data gaps. So how we could use statistics to understand bias and random errors, and how to use expert judgment to improve bias and random errors. So this is like how to improve the accounting. Typical cases to improve conceptualization, we have to go to the basics, the structural assumptions in the quantification. When we are using models, you have to deal and assess the structure of the models and the parameters that are used in the model. Representativeness, when we are dealing with representativeness problems, we have to assess the sampling strategies, apply stratified sampling, improve the sample size. If we use more precise measurement methods, switching to different technologies and measurement technologies that could be improved. If we collect more data that is measured, in general that's related to the sample size, we may expand the sample size, collect more information so as to reduce the random errors and make sure that the random errors are adequately considered in the sample size. To eliminate the risk of bias, this is what I meant before by following the decision trees in the IPCC guidelines. That's why decision trees are at the beginning of each of the sources. If you follow the decision trees, the idea is you will probably or very likely end up reducing the most common bias in GHG accounting and improving, of course, the state of knowledge, understanding better the sector, understanding better the science behind the emissions we are trying to quantify, understanding the categories and what are the key drivers for that sector that delivers the emissions for that category. These are just a few examples. I think we don't have enough time to go through each one of them, but it's just a few particular cases following this how to improve the accounting that you will be able to read it. It's very simple. You will be able to read it on your own when you have the PowerPoint. I'm not sure if you already have it or not, but you will have it. So you can go and see these strategies like better treating seasonality effects or moving to higher tiers to reduce the uncertainty, or using larger sample sizes, or understanding the cycles that may be involved in one emission source, like road vehicles, start-up or full load operations, measurement techniques following some standardized approaches to do measurements of the variables, using some or measure some parameters instead of assuming typical parameters for density, temperature, etc., for transforming from mass to volume. Measuring the data always reduces the uncertainty and the random errors and reduces the risk of bias results. Well, several specific cases, examples on how to implement this improving accounting. And to finish the webinar, a few words about uncertainty assessment, that the focus of this assessment is to allocate resources. The idea is that when we have all the information, we calculate the emissions, and we have the emissions output and the uncertainty. Based on this, we should be able to identify the variables that contribute the most to the total uncertainty of the inventory, of the result, and work and assign time, money, resources, put more effort in better understanding those variables, and not all of them, because it's impossible to improve all variables all together. So with limited resources, it's very important that we allocate the available resources consciously based on information that is useful to do that. Because in the end, the assessment of uncertainty is part of an improvement cycle of the inventories. That's what we are trying to understand. We are trying to understand the emissions, the uncertainty of the emissions, and use this information to improve the results in the future. So thank you very much for attending today. We are on time. There are probably a lot of questions in the chat, which we can deal with those offline. And just, again, thank you for being here 2 hours listening to me. I hope you didn't get so bored, because we will have the whole week ahead for continuing this. Thank you very much. Saben, back to you.
Thank you, Diego. The topic is very interesting and very technical, but we have a time limitation, so we have to stop now. Today's session were focused on review of concepts, technical terms, causes of uncertainty, and how to reduce uncertainty in practice. And I believe that this section will help you better understand the rest of the webinar. Diego, we haven't responded to all questions in the chat, there were some questions in Spanish. So as you said, if you could try to provide some answers offline, that would be appreciated. Today or tomorrow morning you will get the presentation, the PowerPoint presentation. I thank you for your participation, and we invite you to use the same link to join the webinar tomorrow. Same link and same time. So once again, thank you for your participation and see you tomorrow. Bye-bye.